Hello, Business Calculus. So today we're going to continue our conversation that we had last time. Last time we talked about limits. Now we're going to talk about continuity. And continuity and limits are very closely linked in a theme that will be continuing for the entirety of the semester. We will have, the thing we learned from into the very next class. And so for continuity, we use limits to show whether something is continuous or not. So let's go ahead and take a look. First, we're going to begin with an informal definition. A function is continuous if you can trace the graph without lifting your pencil, right? So these are the important things. If you can trace it without lifting your pencil. So I'm going to go ahead and use a blue pencil. Let me go red since I've graphed these in blue. So note along here, if I'm graphing along, I get to this point, I have to lift my finger up and then bring it back down, right? We are discontinuous at that point. And then also here, note, I can go up here, but eventually I got to lift my pencil up and then come back over here, right? We are discontinuous here. And then right here, note, we're coming along. I must lift my pencil, come down to here, and then lift it again, and then come back up here, right? Discontinuous here. Even though the function is defined for all those points, it is still discontinuous. Now we look here, we're coming along. I must lift my pencil to get to here, and then continue on my way. So these are all examples of different ways that something can be discontinuous. All right. Now let's move on to the formal definition. Now that we've got a feel for for continuity, a function is discontinuous if we have this following relation. If we have a two-sided limit, right? Remember, we can only write this right here if we take the limit from either side and get the same result. And if we take the limit and we get the same thing as if we had evaluated, then we have continuities, all right? So basically, in words, this would be if the limit is the same as the evaluation. And when I say evaluation, I just mean, if you just plug it in. I'm going to put that. Right? If those are the same, then it is continuous. So let's go back to the initial examples up top. Note that if I took the limit as x approaches 1, then I get 1.2. But our function, if I evaluate at that point, is undefined, right? They don't equal each other. For number 2, if I say, what is the limit as x approaches 2 for f of x? Well, that's infinity. But if I say, what is f of 2? Well, that is undefined. Right, so they don't equal each other, right? It's not continuous. And over here, if I say, well, what is the limit as x approaches 2 of f of x? Well, that's going to be 2. But if I evaluate at 2, I get 1. Right? They don't equal each other. So on this one right here, you don't even have a two-sided limit, so there's no way the function can be continuous. It will be what's called right continuous, because you can see it's got a solid point on right there. we're going to get into that at the bottom of this handout. So for right now, we're just focusing on just regular continuity. Okay, so we're going to use the formal definition of continuity to identify any discontinuities in the following functions. So when we look at this one, we notice this guy right here, right? X cannot equal 2. We cannot divide by 0, right? Never divide by 0. We can take the limit of something approaching 0, but we cannot actually divide by 0. All right, so 2 is going to be the number that we want to evaluate this at. So the limit as x approaches 2 of f of x actually does not exist. So that's as far as you need to go. If the limit doesn't exist, well then you don't have continuity anyways. Okay. And that's true for regular continuity. One-sided continuity is a little bit different. All right, so let's take a look at this one. We've got x equals 1 and we've got x equals 2, right? Clearly, x cannot equal 1, x cannot equal 2, right? If I evaluate either one of these points, f of 1 equals undefined, f of 2 equals undefined. So it is discontinuous at those points. There we go. And maybe we should go ahead and just spell it out up here. Discontinuous at x equals 2. All right, no problem there. All right, let's go on to the next one, number C, or should I say letter C? Now C is an interesting one, right? It looks like we might have a discontinuity at positive 1. And in fact we do. But let's go ahead and take a look. This is the same as x plus 1 times x minus 1, all divided by x minus 1. Now note, we can cancel these two guys out, but we do have to note that such that x does not equal 1. If I can draw my bracket better. That's a little bit better. Okay, so spell the whole thing out. You'd write this as x plus 1 such that x does not equal 1. Right? It's undefined at x equals 1 because if you plug in x equals 1, you'll get something that's undefined. Let's go through the whole. So we know it's going to be discontinuous at 1, but let's run through this process anyways. If we want to say, well, what is the limit as x approaches 1 of f of x? Well, that's going to equal, we plug it into this expression here, 1 plus 1, we know which is 2. That's fine. Now if I ask, well, what is f of 1? Well, that's undefined, right? The limit here does not equal the evaluated function. So because of that, it is discontinuous at x equals 1. Great. All right, so this next one also is an interesting one. We've got an absolute value going on. We can see something interesting is going on at x equals -3, but why don't we go ahead and kind of crack open that absolute value. This basically is x plus 3 divided by x plus 3 if x is equal to or greater than -3. You might be going, well, why -3? The reason it's -3 is that's where this becomes 0, right? X plus 3 has to be equal to or greater than 0. That's why we picked this number. Basically this comes from x plus 3 must be equal to or greater than 0. Well, that becomes x must be equal to or greater than -3. That is where that came from. All right. I'm not going to erase this, but let me go ahead and change the little blue there so you know it's a little bit of side work. All right, and then we have x plus 3 divided by x plus 3 negative if x is less than negative 3. All right, because that's what the absolute value does. And so we note that this can further reduce to simply 1 or negative 1, all depending on if x is equal to or greater than negative 3, or if x is less than negative 3. Note that this is all contingent on x not equaling negative 3, because that's in the bottom there. So we can go ahead and just take that out right there. Let me go ahead and move this down too. There we go. Alright, so now everything is covered. Note that this is discontinuous at negative 3. So we'd write simply discontinuous at negative 3. Let me show you why, though. The limit as x approaches negative 3 of f of x is simply undefined. Because if you approach from one side, you get positive 1. If you approach from the other side, you get negative 1. They both have to approach the same number in order for this thing to work. All right, and so, and also, you can't plug in negative 3 anyways. The whole thing is undefined at negative 3. So we would say discontinuous at x equals negative 3. And that's it. We did it. At this point, I'm going to ask you to press the pause button on the video. I want you to graph each of these in Desmos.com and see for yourself what these guys look like, and just to verify visually so that you can see it, that these in fact are discontinuous at the points that we have stated here. Okay. Okay, yeah. Yeah, do exactly what I said there. A function f is continuous from the right at a number a if we have this condition here. It's continuous from the left if we have this condition right there. So note the difference. It's right continuous if it fits the definition of continuity from the right. It is left continuous if it fits the definition of continuity from the left. It's basically the same thing we were doing before, only now we're looking at whether or not it is left or right. Alright, so let's go ahead and take a look at this. We're here. Alright, so what we're saying in this problem is that if x does not equal 1, we're going to use this expression. If x does equal 1, then the output is just 1. Alright, so we want to know, is it continuous, discontinuous, what's going on? First thing we note that this, if we're looking at 1, what happens if we take a limit from either side? Let's say the limit as x approaches 1 from the left of f of x. Well, basically this is f of 1 minus some small number. And so we plug that in. 1 divided by 1 minus epsilon minus 1. Let me go ahead and just highlight all the things. So like everything in yellow is kind of equivalent to each other. So you plug that in, evaluate it, you get 1 minus 1 here, and you end up with 1 divided by a really small number, a number that is vanishingly small, and anything divided by something small is really big, so it's negative infinity. And if we go from the other side, the limit as x approaches 1 of f of x, we're basically going to do the same thing, only now it's 1 plus epsilon minus 1. And so you end up with 1 divided by a positive epsilon, which is positive infinity. And then you notice if you plug in the number into the function itself, f of 1 is simply 1. So you can clearly see the limit as x approaches 1 from the left of f of x does not equal f of 1, and neither does that equal the limit from the other side. Okay, so it's a discontinuous at x equals 1. Okay, so for the next one. Alright, so we want to know what's going on at 5. So we're looking here. You know, basically we're trying to figure out, okay, do these things sync up or do they not? So first off, what is f of 5? Well, f of 5 is obviously going to be, this guy here. And so you plug that in, you get 5 minus 5 squared, which is 0. So we do know that at the very least we have one-sided continuity, but do we have two-sided continuity? So we got to look at the other one now. So now we're going to look at from the left-hand side, the limit as x approaches 5 from the left of f of x, and again that's simply f of 5 minus epsilon. And so we've got here, so it means we're going to use this guy. 2 times 5 plus 3. And you notice I'm not using epsilon anymore. It's because epsilon's getting smaller. If we include it, basically we'll just be including 2 times something that's insanely small or vanishingly small. It's not going to contribute anything to our result, so we can just ignore it for that basis. Alright, so when we plug this in, we get 10 plus 3, and so that gives us 13. That doesn't match, right? So it is not continuous from the left-hand side, but clearly it is from the right-hand side. So we can say the limit as x approaches 5 from the right of f of x equals f of 5. Right, that's because we've got an equal to or greater than, so of course it's going to work. So therefore, this would be right continuous at x equals 5. All right. C. All right, so we'll just ignore C because C is just a repeat of number or letter A anyways. So let's go on to D, which is also just a repeat, so we'll just ignore that one as well. All right, so now we're going to look at ceiling and floor functions right here. So ceiling and floor functions are definitely applicable to business applications, particularly when it comes to billing. If you're a phone company, you might use a ceiling function to try and charge how many minutes, because you can include some decimals, but at a certain point, you got to figure out, okay, where is the cutoff? And so the ceiling function simply rounds up. Right, rounds up, and the floor function will round down. And basically these are called step functions because you end up with something that looks like a step. Let's go ahead and take a look at the graphs of each of these in Desmos. Alright, so to get this to graph in Desmos, all you have to do is just type in CEIL, and that will get you the ceiling function like this. And so basically, let's go ahead and zoom in right here. For all the inputs along here, it's rounding up. So if you go 0.1, it rounds it up to 1, right? Even if you're 1,000th over 0, you're still getting rounded up to 1. So if you picked up the phone and dialed, went through, and then immediately hung up, you're getting charged for 1 minute right here. That's how this works. This used to be a lot more common with collect calling back in the day. That's not really much of a thing. I don't know if anyone does collect calling anymore. Maybe they do. But used to be a lot more prevalent than it is now. But you can guarantee something like this is still used for data and other things on your modern day cell phone. AT&T will still get their dollars one way or another. But this is the ceiling function. So if you're getting billed, you don't want a ceiling function applied to you. However, if you are getting billed, you would prefer the floor function, which is just the opposite, right? Everything is rounded down. If you went to 0.99999 minutes, well, you're getting charged for 0 minutes here. But the moment you get past that, then you're getting rounded up. The moment you're at 1.01, so yeah, if you're at 1 on the dot, you're down here. But the moment you go even a smidge over that, you're getting charged for that extra minute right there. All right, so that's how these ceiling and floor functions work. Let's go back to the handout. So we want to know what's going on at 5. Are we left continuous, right continuous? We can already see that we're not, based off of the graph, it's not going to be a two-sided continuity. It's going to be either left or right. So let's go ahead and take a look at this. All right, so you can see that at 5, because that's where the point that we're interested in, at 5, we come up to here. And you can clearly see, let me get to where you can see it. 5, 5, if you come here, you can clearly see it's left continuous. It's not going to be continuous from the right, since it's getting bumped up. All right, so let's go back. But we're going to use our mathematical tools. We're not going to rely on the graph. The graph just helps us understand what's going on, after all. So we're going to say the limit as x approaches 5 from the left of f of x. Well, that's going to be f of 5 minus epsilon. So we're a little less than 5, right? Like 4.99999, 1,000 nines, and then another 9. We're really close to 5. We're not quite there. It's getting rounded up to 5, which is the same thing as if we simply plugged 5 in, right? And so we are confident in saying this is left continuous. And nothing else. All right, so the floor function, same thing. What is the limit as x approaches 5? Only not from the left this time. Now we're going to look at it from the right, because everything's getting rounded down, remember, of f of x. And so once again, this is f of 5 plus a little bit, right? It's 5.00000, 1,000 plus 1 zeros, and then 1, right? Well, it's getting rounded down to 5, because that's how the floor function works, which is the same thing as if we simply evaluated it at 5. And so that is right continuous. Awesome. All right, and there we go. Sorry, I forgot to delete this guy and this guy off the handout, but I don't think that really hampered us in any way. Just make sure you guys practice on the homework. Email me if you have any questions, and have a wonderful day.